The reason why we start from chapter 3 is this is something that related to the module 7 we learned. So I can go quite quickly on the parts we learned before. So module 8, okay, let's start from here. Module 8 is known as something analysis doing something. So when we say, hey, we are analyzing, analysis, we can analyze by qualitatively and quantitatively. Now, Jeremy, what do you mean by if I ask you like, hey, can you qualitatively analyze something? Or if you get a question like qualitative analysis and analyze something, what does that mean by that? Using words, okay? So in chemistry, when I say, hi, qualitatively analyze something, then what does it mean?
Like physical terms.
Yeah, so you gotta talk about what that is, what the chemical. So when you say qualitative analysis in words, you need to identify. So it's more about identification of whatever that substance is. Okay, and you also need to give some good backup justification. So you will get questions like this here. Hey, we have a compound. Let's say compound X, organic compound X here. So when I ask you, hey, qualitatively analyze this means I want to know what that is. Identify what that compound X is. Okay, identify as in like I need to know its possible functional group. Okay, it's a molecular formula or empirical formula from there. Now, quantitative analysis means that you need to determine its concentrations, which is in numbers or moles, or sometimes the mass, any of those. So that's known as quantitative analysis, and we did some quantitative analysis in module 6. John, you did some quantitative analysis in module 6. What was the quantitative analysis process we actually did? And you had a test this week. Titration. Titration known as quantitative. Okay? But it's not a qualitative because we know what's in the burette, what's in your conical fluid before you perform the experiment. The purpose of titration is you're only looking for the concentration, exact concentration. That's known as quantitative analysis, guys.
Are we looking for like the chemicals of the titration?
Mm-hmm. You're always given what that is. I mean, you can't start the titration without knowing what's in that burette, what's in the conical fluid. There's no point. There's no point. I mean, like you're just dropping some random chemical in it, like you see the color change. Yeah. But what's the point of that? Looking at the color change?
You know the concentration.
You can't. You can't even know the concentration because you don't know whether the acid is diprotic, triprotic, or monoprotic. See? You'll be like stupid, like just doing that titration without knowing it. So you have to know the difference between here. For the organic chemistry, for organic qualitative analysis, we're going to learn about qualitative analysis first. And we actually did many of those analyses before. So let's start from this, unsaturated carbons. Chapter 3. We started from chapter 3. So assume that we have unknown. So for the test for the alkenes or the unsaturated carbons. Okay, guys, assume that we have alkenes here. So say we have a test tube of some alkenes. So that's alkene. Jomin, how are you going to test that alkene must be the alkene? Bromine water. So let's have a talk about the bromine water experiment here again too. How would you do your perform the bromine water test?
Method?
The methods, yes. I told you got to memorize lots of methods.
Like, do I give you a method?
Can you give me the method? Can you give me the instruction?
Pour 50 mils of alkene.
So 5 or 50 mils. Yeah, 50 mils is quite.
15 mils.
15 mils, okay, acceptable, okay.
15 mils.
Just 5 million.
5 mils, good, okay, because you're going to use a test tubes. Test tube, you're going to use a test tube. So test tubes is only be like, pouring that 50 mils in here, overflowing, and alkene means it's like flammable. So maybe like 5 mils or like 10 mils will do, okay, reasonably. It's given a 5 mils in your workbook, so you can follow that. You prepare the 5 mils of alkenes, and then what do you do?
Add 10 drops of bromine.
Well, that, okay, maybe 10 drops, okay, maybe a few drops, maybe a couple, like a few drops of that, okay? And then what do you expect?
Color change.
Color change. So for the bromine water experiment, bromine plus a Br2 in aqueous bromine water experiment, the expectation you get is if this is alkene, you to see that the color change, yeah, color change from like from brown or yellow to the colorless or decolorizations, colorless, from that too, yeah.
So it's the only bromine water that's changing color, right?
What do you mean?
Do they both change colorless? Like alkene and bromine water?
Just bromine water.
Just
It's a
bromine
mixture
water.
now.
But you're
It's a mixture.
Well, like,
You're looking for the color change of bromine water, isn't it?
No, you're looking for color change to what you have in a test tube. Guys, this is why I'm asking you like instruction. You prepare the 5 mils of the or whatever the solution is. You pour some. Bromine water comes out. Okay, bromine water itself comes out in the reddish or the yellow, brownish colors, which is look like this. That's the bromine water, basically. Okay, when you get the bromine water, that comes out the brown, and when you're putting the brown bromine water into the alkene, that just goes to decolorize. Basically, there's no color up here. It's colorless.
well, alkene also changes color, but it's not like colorless.
Then what?
I don't know, because when I did the experiment at school, there was like some weird color, like cloudy color, was it?
That means that's been contaminated.
Oh, so both of them have to.
Cloudy means there's a precipitation ongoing. So I mean there must be from the previous experiment there left some metal in it, so that making the precipitation with the bromine. So that's what we expect, guys. The brown color of the bromine water immediately decolorized due to the alkene react the bromine water by the additions too. So that's what we're looking for when you have alkenes in it. You must know the methods for every single process that we're going to discuss today. Yes, Jeremy, this is why you need to study this week. Not next week, not week after. It's going to be too late. There are more contents coming in next week. Okay, so study every week consistently. Method of that, expectation. That's very important. You get it?
What do you mean by study? Like memorize?
Yeah.
Just keep going.
Keep going.
Memorize.
Do your homework, finish your chapter exercise, revise that, the methods, study for your test coming in 2 weeks too.
So just memorize that, learn 3 dot points for bromine water.
Yeah? Easy, isn't it?
hard.
It's so hard, okay? That's one way we can test for the bromine water. Now, second method, we can test for the alkene. Whether we see qualitatively test for the alkene is, we use something called using the acidified potassium permanganate. Oh, what is this? Yeah, what's this? Acidified potassium permanganate. I can write it as Mn. Catalyst? Catalyst? No! This is known as the very strong oxidizing agent, making something to be oxidized. What's the color of this, Jeremy? You did in year 11, permanganate. Purple. So when this goes to oxidation, what we call the change? Purple too. Again, colorless. Here again too. So if we have an alkene present, okay, if we assume that it's alkenes, I know permanganate can be used used with oxidizing agent for the alcohols too. But just like an alcohol, we can use the acidified potassium permanganate or permanganate to see the oxidation of the alkenes. So what you see there is the purple color of the permanganese, it will get changed or decolorized if we have an alkene present in here. If we picking up number one experiment for the alkene, I would pick for the bromine water, because this has a limitation that this acidified potassium permanganate also working for the alcohol. We're going to discuss about alcohols later too. But if you don't have any option, if you don't have run out of the bromine water, you can use that. Okay. Yeah, so that's the reaction of that to making the alcohol structures. Any questions about test for the alkenes? Something that we did before? All right, then let's do the test for the carboxylic acid. Jomi, what would be the methods that we can qualitatively analyze the carboxylic acid? Qualitatively, how do you know that unknown compound? Assume that we have unknown compound. Assume that you have given this kind of bottle here. I want to test that whether this is a carboxylic acid or not. How can we do it? I just want to test that whether this is a carboxylic acid or vinegar or not. You never, right away, you never taste it. There are some people say, "Can I taste it?" No.
Smell.
Yeah, smell maybe, but does it kind of confirm you that that's a carboxylic acid?
It produces like, is it esterification?
No, what? That's too far. I mean, this too hard.
Well, it works.
Guys, carboxylic acid is it working as a what? Acid or base? It's an acid. So can we do the pH test? Qualitative. You can do the pH test or the litmus test.
Like just dropping the.
Drop what? We collect the sample and put the some litmus paper. So what litmus paper? If this is acid,
Blue.
bar. Remember that. Blue turns to red for the blue the acid. Bar.
Huh?
Bar.
Oh, why is it acid?
Acid.
Oh. Oh.
Bar is how you remember.
Blue acid turns red.
Blue acid turns red. Yeah.
Oh, yeah, okay.
Or RBB is something that you can do. Red turns to blue for the base. But just go for bar. And if you know the blue turns to red, the other one will be the base in here. All right, that's one test we can do. Anything else? Thinking about the carboxylic acid, it's a weak acid. It's a weak acid. So is there any like a chemical test we can use to determine that this is a carboxylic acid or the weak acid? Jeremy.
Reaction.
Yeah.
Like, if it's an acid, doesn't it react to like the powder? Sorry,
What powder?
the bicarbonate, right? Bicarbonate.
Bicarbonate.
Or
Okay.
sodium carbonate.
Sodium carbonate. And what do you expect?
So like kind of fizzle and then die out.
Hmm?
Like if you had an acid and you pour it in,
Yeah.
and it sort of fizzle,
Fizzle.
like bubble,
Bubble.
like
Can we just use the word the gas is produced? Okay. Bubble gas is produced. Okay. And how do you know that's the gas we were looking for?
you can
It's carboxylic acid.
The reaction with either be carbonate
lime
or the HCO3, so that's known as bicarbonate or hydrogen carbonate, and that if we have the acid that must be reacting with this, because what we know is carboxylic acid with this carbonate or the bicarbonate would produce that salt, water, and the CO2 gas. Bubble, yes. Jeremy means that the CO2 gas will be produced from that too. It's actually shown on your page, that page 107 here as well too. The bubbles of the what? Is a gaseous state of the CO2 gas, CO2. Then how do we test for the CO2? I mean, the gas could be like hydrogen gas. Gas could be yes, we used there for test this, we use something called the lime water. John, do you know what the lime water is made of?
Limestone.
What the limestone is made of?
Lime.
No. It's made with the calcium carbonate.
when you produce gas, doesn't it kind of escape into the environment?
Yes, so this is why we kind of captured. But you can put the kind of small balloon on it. So you will capture those CO2 gases, which is kind of evaporating from the solution. You capture that and pour that gas into the conical flask of the calcium carbonate solution, which is lime water. And if this is CO2, what do you expect?
Lime water turns milky.
Milky or murky, like it goes milky because they form the precipitate of the calcium carbonate. Yes.
Is refluxing only kind of established?
It could be used in the various other experiments, but for the module 7, yes. Reflux simply means you use the condenser. So in that case, we need to use the condensers. You know, it could be many.
It's like a reflux.
Reflux coming forth and back, like using condenser.
So like a mixer.
You're basically like cooling down while you're making a slower process. You're like gradually producing that too. Okay. Anything else for the calcium carbonate? I mean, bicarbonate is given in here. That's the very kind of famous. So methods is given on your page 107. 5 mils of the carboxylic acids, like it could be a sample of the carboxylic acid placed in the test tubes. Carefully and add a drop the sodium carbonate solution, and CO2 gas bubbles will form in the presence at the of the acid. The identity of this gas can be confirmed by bubbling through the lime water. It will turn the lime water milky. That's the sample methods for this identification of the carboxylic acid. Okay, this is how we test for the carboxylic acid. Any questions about tests for the alkenes, unsaturated carbon, or tests for the carboxylic acid? Pretty easy. Okay, now let's do the third one. The test for the alcohol. Tongyu, how are we going to test for the alcohol? How can we test for the alcohol? So assume that we have a known compound here. We're kind of curing like, oh, this might be the alcohol. Maybe you can smell it, like it smells like alcohol. Maybe like, okay, it's giving, yeah, but you can't drink it. You should not drink it. The only alcohol you can consume, you can digest is the ethanol. If you drink methanol, by the way, you get intoxicated, you get brain damage straight away.
Bro, can you do like
Yeah.
flame it up?
No.
Yeah, just burn alcohol. Yeah, just burn.
Everything here will be burnt. I can save it too. Yeah, and you never ever use the flame. Okay.
Flame test.
Yeah. Good luck. Okay. Alcohol. How can we test for the alcohol? So think about alcohol. It has OH. It's OH. It's not actually working as a. So think about what I mean the acid and base here again too. Acid means proton donor. Base means proton acceptor. So OH is somehow is something working as the OH can be donated. Yeah, it can be working base or like acid too. So actually alcohol is a slightly, this neutral most likely, but slightly be acidic. So one way we can test for that slight weak acid is we use something known as sodium metal test. So what we do is we put some little piece of sodium. So you will see there's something reaction like this, page 109. It shows that the sodium metal in the presence of the alcohol, sodium with the alcohol will produce that salt solution with the H2 gas produced in here. Do you remember the acid and metal reaction? Acid and metal reaction produce the salt, leaving salt and the hydrogen gas. So just same as that in here. The only test, yeah, we use the pop test too. So that can be used to identify the pop test. The reason why we use sodium is known to be one of the most reactive metal. So you saw that sodium can actually burn or combust it in the water too, by producing lots of the hydrogen gas behind. So sodium metal is the one we can test here. Some people ask me like, oh, can we use sodium metal for the carboxylic acid too? Yes, you can, but the problem with the reaction between carboxylic acid and sodium metal is they are so combusted. They are combusted straight away. It's quite risky. Okay, so before you test for the carboxylic acid, you actually burn your lab. So you don't test carboxylic acid with sodium because they're so rapid, so radical. Okay, so but alcohol is slightly more like a weak, like almost like a water, like a neutral. So it will be reacting with the sodium metals, kind of like a gentle manner.
Isn't sodium in like They say don't chuck like blocks of sodium into like rivers and
Yeah, I mean, you will see like it's actually combustion. This basically you're bombing.
like.
You're bombing.
Yeah, then why are you doing it in alcohol?
We do like a liter piece. This is why. And thinking about the structure of the alcohol compared to water, water has a two of the bonding, hydrogen bonding can be formed. But alcohol only has a one in here. So compared to the water reaction, this is more gentle. So we only see the hydrogen gas, but we never put the block of the sodium into the batch of the alcohol. We never do that.
Block.
Yeah. All right. So this is one way. Now, how do we then test for the alcohols in their degrees? Show me. How can we test for the primary, secondary, or tertiary states? This is related to the module 7 here again. Oxidation. Tell me more about the oxidation. What do we use for the oxidations?
Like you can use like KR2O7O.
So acidified potassium permanganate or acidic potassium dichromate. Jeremy, how do you write the acidified permanganate?
Just there.
Just write KR2.
Acidified permanganate.
MnO4.
H plus. Acidified, it means acid. MnO4 minus O.
CR2.
Yes, Cr2, O7, 2 minus. Memorize that too. It is something we memorize in the year module 7 here again too. Now, let's see then. Ian, if I put that into unknown here, what do you expect? What do you expect?
A reaction.
Reaction, yeah? In which case will it have the oxidation reaction?
First and secondary.
First and secondary. So we only see the reaction in the first and secondary. So for the first primary and secondary alcohol only. I mean, there is a difference between their time as well, how fast the reaction happens to. Primary will be the fastest. It happens really quickly.
Yeah.
Secondary takes a little more time. Okay? You all right?
Yeah.
Okay? Wake up. Permanganate. Then what would be the color change of permanganate? The permanganate solution is a purple. Purple, so if there is an oxidation, you would see the color change from purple to the colorless.
Why?
Because they're oxidated, maybe you're losing the color of the permanganate.
Do you just memorize that?
You memorize that. It's actually given on the page, on the next page in here, showing the color changes. That's what I mean by the purple to the colorless. Okay? Now, when you're using the dichromate, you would see that yellow, it's actually yellow or orange. Depends on the concentration. Some textbooks describe the orange, some textbooks describe the yellow or yellow-orange. Turn it into the green if there is the oxidation. This is only for the primary and secondary. But, does it tell you specifically which that is primary or the secondary? Can we differentiate that, like in the primary, secondary, so we can exactly qualitatively get what that alcohol degree is?
Well, it's different colors though.
I mean, like both of them, it's either this or that.
Like ketones are.
But how are we going to test for ketone carboxylic acid? There's one way. Maybe we can go back to the carboxylic acid test. Maybe one way we can do so. But let's do the quicker one. Like I want to quickly check that whether that's primary, secondary, tertiary, because I don't have much time. Okay, how can I do it?
Check if it's a ketone.
Check is. I said that's the long way. That's a really long way. So the quickest way is we use something called something called zinc chloride with the HCl. Okay, and we kind of learnt about in the kind of the substitution reaction. Using the zinc chloride means we're inducing some substitution of the alcohol to the chloride. So what do you expect for that is, for primary, there's no reaction. It's forming the haloalkane. So primary alcohol would not have the substitution reaction with the zinc chloride, the hydrochloric acid. Secondary alcohol, we have a really slow reaction. So how do you determine the reaction? You actually see the precipitation. It goes kind of cloudy. It's shown on the page. Example is shown on the page 111 here. That's how we determine there's a reaction. There are layers. You will see that the layers, okay, of the layers of the alkyl chloride and the water. That's how we can determine the presence of the presence of the reaction here. If there's no reaction at all, you will see that this will be just colorless solution. That's I'm talking about the first the primary alcohol here. Now secondary alcohol, it's got to be really slow. Slow as in like it takes an hour. It takes an hours and hours to make that kind of forms. But there will be some reaction. Now tertiary will be it's really rapid. Rapid reaction, really fast reaction, means that for the tertiary, if you have a tertiary alcohol in your test tubes, putting that zinc chloride and hydrochloric acid, you would definitely see the layers really quickly.
Why?
Because tertiary alcohol is the most stable form, holding carbon and this form too. We discussed that before.
This is not oxidation, right?
This is not oxidation. That's a substitution.
But the changing color, purple to colorless, that's the oxidation.
That's oxidation. Now, combining these two then. Oh, Ian, tell me. I assume that I have a tertiary alcohol. Tertiary alcohol. So let's assume I have a tertiary alcohol here. How are you going to test for tertiary alcohol then?
We did how do you know this is tertiary?
How do you know it's a tertiary?
Well, first you test if it's. We test if it's. Can we just use your zinc chloride? Zinc chloride and.
Yep, that's the first. We can use the zinc chloride and hydrochloric acid. And what do you expect if that's a tertiary?
Rapid reaction.
Of
Becoming cloudy.
there will be a layers of the cloudy and the water too, by forming the alkyl halide behind too.
Yeah.
Rapid reaction. Anything else?
You know, do we have to test the using catalyst?
What catalyst?
Not catalyst. Magnate.
It's either this. You can either use this and that, but if you're using both, if we assume that we have tertiary alcohol here, oxidizing agent would not react. So you would see that the purple color of the permanganate still be purple. Dichromatic color of the yellow-orange would still be yellow-orange if this is a tertiary alcohol. Okay, you can confirm that the tertiary alcohol using the zinc chloride and hydrochloric acid, that if I put these zinc chloride and hydrochloric acid in here, there'll be a rapid formation of the layers of the precipitate, or like murky, and some layers of the cloudy of the alkyl halide or alkyl chloride with the water on the top.
Alkyl chloride is just haloalkane.
Haloalkanes, or in terms of the alkyl chlorines or chlorides attached.
Can we just do the zinc chloride reaction then?
You can, but you probably get. The question is, they're giving you this one too. You need to know both. You need to know both.
Isn't just using that. So you first do the zinc chloride reaction, and then you do the permanganate just to make sure.
Could be. Yeah, the question could be like this. They can ask you, hey, we perform the oxidation. There's no color change. Okay, so what would be the second method you can use? It could be various. So,
If there's no color change,
of what?
like using Z and CO2, wouldn't it be just first?
But most likely be the first primary alcohol, but it could also be secondary because it takes a long time. It takes a long time. So if assume that you only have 10 minutes, you can't test for that. So what are you going to do? You're going to do the oxidation test from that too.
That's the second one.
You got to combine the results of those two.
But wait, for the second method, I thought you couldn't tell the difference between the first one and the second one. Like
Oh, it takes a long time. Means it starts slowly forming some layers.
the second experience for the
What do you mean the
primary and
second?
secondary.
Yeah.
You can't tell the difference, can't you?
For the first one, oxidation, no,
You can't.
no. It's kind of same. So it's summarized in table 1 given over here, guys. You can see the reaction with the sodium metals, potassium dichromate, say orange. Yeah, it says orange. That's fine. Okay, orange to green for the dichromate for the primary and secondary. Tertiary, no reaction, means no color change. Permanganate would be changed from purple to colorless. Zinc chloride would be no reaction for the primary. Secondary, there'll be slow reaction forming formation of the second separate layer. Fast reaction for tertiary, forming that layers really quickly. Yes, John?
But you know, like we're testing for alcohols and then we're testing again. It's secondary or like primary.
Yeah.
Like once you like when you're testing for alcohols, then you add the thing and add on what is it? What do you add? To test, was it? Na. When you
Sodium.
add Na initially to test if it is an alcohol.
Yeah.
Wouldn't that like affect like to check for first degree, second degree?
Oh, you extract. You get this, collect the sample.
You can just take Na out.
So what do? You don't dunk everything in here. You collect a sample of 5 mils. So when you're writing a method, you actually need to indicate that you collect a sample for each of the different procedures. Yeah.
Oh, okay. So like little bits at a time.
Yeah. Guys, method is need to be practical. It needs to be practical. Practical as in like you need to mention like the actual like volume you're going to extract, you're going to collect, what tools you're going to use. So test tubes in that case most likely. And how many drops? Well, like say 3 or 5 drops, that's fine. Okay. Now, another method we can use is using the phosphorus pentachloride. It's something we don't really use a lot, but it also can be used. All alcohol react the phosphorus pentachloride being tested. It's important that the exothermic reaction follows produce hydrochloric acid here. So alcohol with the phosphorus pentachloride produce hydrochloric acid. And how do we test for the hydrochloric acid? The gaseous state, we use the litmus paper. Turning blue litmus to red here again too. So there's a gas present in here. We don't know what the gas is. You can use the various tests to confirm what the gas is. For the CO2, of course, we use a lime water. For the hydrogen gas, we use a pop test. For the hydrochloric gas, guys, this is why you never ever smell that gas. Okay. Hydrochloric acid gas means it can damage your nose cells quite quickly, or nerve cells even. You never smell it. This is why we don't really do that in schools, a lot of this, because it can be quite risky. But that can also be used. It's good to know. But mainly we use these methods here, mainly. All right, now 3.1, question 1 here. Describe how you could test if a compound is carboxylic acid. What result would confirm that the substance being tested is a carboxylic acid? Tongyun, what would be the test we can use for the carboxylic acid again? pH test, okay. But anything else?
Reaction with CO3.
Okay, I would definitely go for the reaction with the sodium bicarbonate. It'll be the aqueous or the solid. Generally, we use the aqueous because it has a lower number of the moles. Putting the solid baking soda into that could be too reactive. So we generally use the solution of the sodium carbonate or the sodium bicarbonate. Either these two. Then how do you know? Yes.
If it says describe, do you have to write a method?
Yes, you do.
Can you, wait, can you explain it one more time? Why you use sodium carbonate? But didn't you say so that you do it carefully, right?
No, I said, focus. I said we don't generally use this powdered sodium bicarbonate because that would be too reactive.
Yeah.
You can imagine like putting that, like gases coming out from that. So what we do, we make the solution of sodium carbonate, or we have some sodium carbonate solution ready. We kind of mix gently so that the gas is coming out. Okay. Then how do we test for the gas again? Lime water test too.
Did we do this in year 11?
You probably did. I mean, you did that in like year 12 as part of some of the experiments. Year 10, from year 10. Guys, this is year 12. End of year 12, by the way. End of year 12 means you can't get anything from year 10 to 12.
Can you So litmus paper can only be blue, right?
Yeah, so that can be limited in that case. I mean, litmus, yes, it may be, but it's not really confirmed that weak acid. It does. It's kind of weak evidence, but still use the pH test.
So if you got like blue litmus paper,
Yeah,
you add acid
Bless
to
you.
it, it's just gonna turn red
yeah,
all the time.
all the time. For example, water would not make the color change because the pH is 7.
But water could be both. as well.
Yeah, water because pH is 7 for that. Okay, describe means, guys, you need to write the methods. This is what I mean, like you can get questions like this. Okay, let's have a look at question 2. How would you confirm that unidentified liquid is the alkene? How would you do that, Jongmin? Bromine water. So you do bromine water test. Anything else? Anything else?
Potassium manganese.
I do this. It's given on the board here. It's been there. This is the answer. But mainly we use the bromine water, as I said. Acidified potassium permanganate can be also used to identify the degrees of the alcohol. Okay, so to confirm that, but this alcohol would not react with bromine water. That's a thing. So we use bromine water for this. And how do we do the, what are the expectations? If this is alkene, if that compound is alkene, the color must be changed from brown or yellow, brownish yellow, orange to colorless. That's the expectation. Easy. Okay,
This is all method, right?
it's not a method. 3.
All this space.
Trick. An unknown liquid is thought to be an alcohol. So how could you test for the presence of the hydroxyl functional group? Jeremy, how are we going to test for the presence of the hydroxyl functional group?
Use, I guess, acidified potassium permanganate.
No. For the hydroxyl functional group? How do you know this is the alcohol? It's simply just the alcohol. How do you know?
You don't have to care about the degree, right?
No. I just want to know it has OH.
Na.
Sodium.
Yeah, we use sodium metal. And what do you expect? Adding some sodium.
Gas.
What gas?
Hydrogen.
Hydrogen gas. How do you confirm the hydrogen gas? Forming that H2 gas. And how do you test for the hydrogen? How do you confirm the hydrogen gas?
Pop test.
And use a pop test. Confirm the presence of the H2 gas. That's how we do it. Okay? So the reason why we're learning like this many here, you will get questions like a puzzling. Do you remember the questions we had? The practiced one? Okay? Yeah, you will get the puzzle question. You get the flow chart or some sort of like some like methods, and you got to identify what the compound is. But yeah, this is why you need to memorize all the expectation colors and sometimes be methods. Okay? B. Describe how you could determine if alcohol is a primary, secondary, tertiary alcohol. Can you write the method for this name, please?
Method?
Method. Describe. Method. Yes.
We did both method, like.
Describe.
Okay.
Give it a go. Give it a go. We did that.
So you can either.
You can have to write the actual method. So when I'm looking your method, I should be able to perform that. I should be able to perform that and then get the result, valid result.
Those are aqueous, right? Zinc chloride and HCl.
Yeah.
You can use either of those.
No, both of them. Yeah, both of them. That comes in the package.
Do you use a test tube or beaker? Doesn't matter.
For the
It does.
ZnCO2 and HCO,
Hmm?
how much are you meant to put in?
Say again, sorry.
For the ZnCO2, how much are you meant to put in?
What volume would be reasonable?
3 to 5 drops.
A few drops, yeah. Yeah, maybe.
I don't find it.
Isn't it like an aqueous solution?
There'll be aqueous solutions. Yeah. Yeah.
Can you do like decimal ratio?
Because we just want to know whether this is primary, secondary, tertiary. We just want to test them. Test them. Test them. This is important. We don't use beakers to test something.
Do you have to mention like the 15 mil test tube?
No. Test tube will be like just like most likely the same, like one size only. Like this is test tube. I don't really measure the test tube means generally test tube doesn't have the volumes like it has like a 10 mils volume of course, but don't make it like, oh, I use 100 mils of the alcohol in that test tube. That doesn't make sense. You're basically overflowing all the alcohol. So I can't do that. This is what I mean by your method must be the practical. So use the practical tools like the test tubes here. So probably the ideal amount we use for test tube would be 5 mils.
Is it bad if you say 4 equal amounts? Or do you have to be specific?
What do you mean the equal amount? And what?
Equal amount. It's equal amount of okay.
Tell me, would it be like, okay, I don't get it. Like you just need to test that whether your alcohol, this one, is primary, secondary, tertiary. Yeah.
Do you mix
So
it?
mix
Zinc chloride. Or do you just
more like maybe like you can just say pour, right? Yeah.
Just like, how do you differentiate between primary and secondary? I feel like memories.
How can we do it? I mean, it doesn't say like your time. Like there's a time limit here.
Huh. It's just wait 1 hour.
You like it's not like after 1 hour you suddenly pop of the layers. You're gradually seeing the layers are forming. That's mean the slow reaction. Okay, but for the primary using the zinc chloride and hydrochloric acid, you won't see any of the reaction for like So if you see nothing happen in say 10 or 20 minutes, that's kind of confirming that must be the primary alcohol. But if you gradually see this, you're seeing the slow formation of the layers. Okay, that's the secondary then.
So would you do the permanganate test as well? To make sure that
You can.
but you don't need to.
Well, it's not a compulsory.
Okay.
He's a rat.
What happened? What happened?
Look at that rat out there.
Yeah, what'd you get?
He's a rat. All I see is a rat outside.
Now, what was that rat doing outside?
Johnny, how would you describe your method?
1. Pour 5 mils of solution to 3 different test tubes.
Okay.
2. Add 3 to 5 drops of zinc chloride / hydrochloric acid.
Yeah.
3.
Solution, you mean?
Solution, right? Yes.
Mm.
3. Observe. If no reaction occurs, it is primary.
Yeah.
If reaction occurs slowly or gradually within an hour, it is secondary.
Good.
If rapid reaction occurs, it is tertiary.
Good.
Is it necessary to use 3 test tubes?
You can use 1. Actually,
Yeah.
You just like one.
oh,
That's why I was like, what do you mean the equal amount? You only need one.
oh,
No, actually.
You only have one. You only have one. Okay, it's not the 3 solution you have. You only have given one bottle here.
Yeah, but you can transfer it to 3 different test tubes.
Why? What for?
No, I did 2 because the first thing I did was add like a bit of CR2.
Okay, yeah, you can do this one first. Yeah,
And
I
if
accept that.
Turns like then if it's remained yellow, then it's tertiary.
Good,
And then I did.
good. Unless you're doing the separate set of the experiment, different experiment, you don't need to have 3 different test tubes.
would I like lose a mark?
Yeah, of course.
I'm not wrong.
But I know you're wrong. That answer is not right.
Inefficient. Not
You're
wrong.
very inefficient. Like if I just follow your method, I need to use 3 identical test tubes without any reason. Do you get what I mean? Yeah. But if you use one of the test tubes to test for this, okay, I was expecting that actually. Pour one permanganate, pour one with the dichromate, pour one with the zinc chloride there too. If those results are matching to very specific degrees of the alcohol, for example, if that's a tertiary, if this is tertiary, using that permanganate, we'll see like there's no color change from purple to purple. Dichromate would no change at all from yellow to yellow here again too. But for the zinc chloride, use a rapid reaction of forming the layers for 3 different test tubes. See that? Yeah. Okay, that's what I expected when you say, oh, equal amount of test tubes. But if you only perform with this one, you don't need 3. You don't need 1. Yes.
When you measure the alcohol, what do you use? Like which equipment?
You can use a spoil. You can use a measuring cylinder. Pipette, no. Like test. For the test, by the way, guys, we don't need to be exact in amount because we don't really care about the concentration here. And test tube is not a tool for the quantitative analysis. You never used this for titration, did you? The case we're using some very specific tools, like a measuring cylinder, or even the measuring cylinder is not inaccurate. We use pipette or burette. Yeah, that we only use for the quantitative analysis there too. So see, this is the reason why we don't use beaker.
Yeah.
Yeah.
So it's small pipette and what spoil is different.
Spoil, like yeah, of course, spoil is not really accurate. It only gives you like certain like estimated amount. Yes.
No, isn't like electronic scale more accurate than what is it? Like burette or pipette?
Maybe, but do we use that? No. So guys, just your method should like it doesn't have to be really fancy or really long. It just needs to be like an instructional otherwise too. So yeah, you can use that. Like I like how you wrote your the methods, except the 3 test tubes. Okay, except the 3 parts, but you know it needs to be just in a short sentence. It doesn't matter. Okay, and write it down the expectation from there too. 4. 3 bottles labeled A, B, C are known to contain either butane 1-ol, butane 1-ene, and propanoic acid. Write down a procedure that could be carried out to determine the contents of each bottle. Yes.
Is it bad to make a flow chart for this type of question? Simply, like,
You can use it for your planning, but you won't get any mark for the flow chart.
Oh wait.
Oh yeah.
So you gotta do.
You can use it for planning. That's good planning. But that's only be planning. You get what I mean? Guys, practice the writing method, guys. You will definitely get a method questions. And you did in your practical test, didn't you? Yeah, I told you, you're going to get some method question at least twice. And you possibly get method question in your trials, even in the HSC these days. Get.
Like another metal test, right? Metal test.
Yep.
Do you use like this kind of bowl, another test tube?
Petri dish. You can use a beaker or the conical flask. But I definitely I will go for beaker because it has a longer neck and wide and longer neck. So easy to put the sodium metal in it, and it can protect you.
Do you have to like mention the state quantity of metal?
Yeah, like don't just put kilo. You know what I mean? Like, don't put the kilo of the sodium into the 100 mils. Be reasonable again. Reason as in, like, only be like 1 gram, maybe 1 gram of the sodium metal will be required just for the test. Again, this is not a quantitative, so it doesn't have to be exact amount. You can even say like small piece of the sodium can be added to.
How long should your method be?
How long is your method?
It's very short now.
It could go up to like like up to 8 to 10 steps, because you need to identify 3 of them. Yeah?
3 steps.
No. This time again, you need to collect the samples for each different procedure. So I'm expecting for each of the identification, you need to write at least 2 to 3 steps. And the first step must be always be collect 5 mils of each sample.
Can you read mine?
I'll write mine here, compare that to you.
Mine's like really simple.
Oh, you
But
should.
then I think it works. It should work.
Okay, compared to your mind. Collect the 5 mils of the A, B, C into the test tubes. Each of those, okay, and then let's test for the butane 1-ol, butane 1-ene, and propanoic acid here. So kind of differently here. So the way we can test for, let's go by order. It doesn't have to be in order. I'm gonna test for the bromine water. So add the 3 drops or 5 drops. Of the bromine water. On each test tubes. Okay, there will only be the color change from brown to colorless only for we have butane 1-ene, use that, or we have butane 1-ene. And others, there will be no color change. Okay, that's done. So this is my 3 steps.
That's like my whole.
Yeah, exactly. I'm like, how'd you do it then? 4, discard all the samples. Yeah, discard all the samples. Discard all the samples. Or you don't have to rewrite. That's collect. You can collect the 5 mils of the new samples.
Or is it like one consecutive experiment?
Yeah.
So I was gonna do like 1 to 3, then 1 to 3, and 1 to 3.
Oh, but you can do it. Sorry, like, and you can write like testing for the butane 1, testing for that, testing for that. You can write that too, or you can either write like these consecutive here. But in every single time, you need to say collect the few mils, collect the samples.
Collect and prepare is the same thing.
Prepare what?
Prepare 5 mil of
Oh yeah, you can say the prepare 5 mils with new sample into the test tubes. Again, like in this case, depends. Like we kind of say, imagine that you have unlimited test tubes here, so you can just use whatever. And what you do, I want to test for the butane 1-0 and propanoic acid. Now, this is key. Guys, how are we gonna test for the butane 1-0 and propanoic acid?
Same time.
Yeah, because we got the butane one in here.
Is it the acid and base?
CH3 2 minutes.
Again, alcohol can be working slightly acidic, so there could be a chance it forms some carbon dioxide too. So it's not like 100%. I mean, like if there is something leaving you behind, like oh maybe that, maybe there's no maybe in qualitative tests. It must be definite. Okay, Chongmin, what was your third step?
Add 3 to 5 drops of boiling water.
Oh, that's
into
your third
each
step.
solution.
Okay.
If solution, oh, mine's kind of different to what you.
Okay.
Sorry.
Then how are you gonna identify, differentiate the butane 1-0 and butanoic acid?
From butane 1-0.
Oh. You can't use carbonate. You can't use sodium metal, because both of them will have a very similar result. Yeah.
My
Alcohol can have the kind of carbon dioxide form too. We can.
I mean, the sodium metal carboxylic acid will also produce.
Yeah, of course. Of course.
Well,
Of course.
So you can't use CH3 2 months?
You better not. You better not, because again, alcohol can react with some of the some of the carbonate, produce some carbon dioxide. Yeah, alcohol it can as well too. It can. It's less likely, but if that's a maybe, I would look for something very very
The
definite.
pH test.
Depends on concentration again. That can be varied. So it's not.
Can we just do the alcohol test?
Can we use alcohol test? What did I say about putting the sodium metal in the carboxylic acid?
I mean, like, permanganate.
Oh, we're getting there. What happened if you're putting some acidified permanganate into carboxylic acid?
It doesn't.
It doesn't react. Guys, remember that carboxylic acid was actually last stage of your oxidation. There's no more reaction. Okay? But what about if that's not primary? This is why they're giving you extra name over here. What is butane 1-0? It's a primary. There we go. It makes sense now. You gotta add a few drops, or say 1 milliliter, or say 2 milliliter of the acidified potassium permanganate.
Do we have to mention acidified?
Of course, of course, of course. Acidified is actually part of that oxidizing agent here. And what do you expect? There will be no color change, or blue or purple for the propanoic acid.
Can you memorize that?
Memorize what?
There is no reaction.
Between?
Color change.
Between?
Purple. I mean, when you add propanoic acid into acidified.
In stage you have now, that's a common sense now.
Is it?
Of course, because we learned that
Oh yeah.
carboxylic acid is your last stage of the oxidation. So there will be no further reaction, isn't it? This is how you think. Use something on your head here. Use that. Don't use a muscle memory. Use this. Yes.
In my method, I included like that one and the line water test. So it wouldn't matter because from that test, we can identify the like alcohol and the carboxylic acid. Propanoic acid.
I don't get it. Why do we need to do lime water test?
Just for like accuracy.
No. Like I'm asking you, we discussed that butane 1-0 can react with the carbonate. It can react carbonate, it produce carbon.
We can distinguish between the other third one, the good one. So you can like make it.
Yeah, but isn't that shorter?
Yeah, but still.
Isn't that shorter? Jongmin, 7 steps. This is mine. I told you it's gotta be about 7, 8 to about like 8 to 10 steps. Depends how you write your methods. So butanol would react with the strong oxidizing agent, therefore change color, change the color.
But that's like this is not a method, right? Because like if because method has to start with.
Because that's what how we can identify, describe the method here. Question asking describe the procedure. That therefore how we can identify that. The color change the color from purple to colorless. Or you can say decolorize the purple color of the permanganate. Okay, something very similar in the HSC does in these days. Or like your skills tests. If you get a skills test again, yeah, it's possible.
Why didn't you use the litmus paper to find proper acid?
Oh, good question. If your carboxylic acid is extremely diluted, module 6, let's go back to that. Module 6, extremely diluted, like say 0.0001 molar of the acetic acid. What would be the pH of it? It would be 7.
Oh, that's it.
Almost like a 7. So do you think the pH test using that litmus could be reliable for the diluted acid? I don't think so.
But then if it works, it works.
Hmm?
If it works, it's good, isn't it?
But how do you know it's gonna work? Are you?
Just so really good. It takes 2 seconds.
Of course, I know. Yeah,
And then
but
you see, and then if it works,
but-
propanoic acid, you get that, and then you put.
What if we
propanoid
don't?
into it, and then it's.
Jongmin,
all good.
what if the color didn't change?
Then you have to do the long method.
Exactly.
But
Then
there's no-
why would you waste your time doing that something
Waste 2
uncertain in
seconds
here?
dipping litmus paper. Waste 2 seconds with a chance to.
But think about
Say-
you're the one. No, you're the one writing the method. You're not the one performing that. I know the performance is really easy, but writing the method is a different story here. You need to write the 3 extra steps. What if? Okay. All right. Next one. We have the propene, cyclohexanol, and butanoic acid. John, how are you going to test them? Propene, cyclohexanol, and butanoic acid. Can we use the same method as this?
You can use the bromine water.
Yes, we can use a bromine water test. Yeah.
Is
Cyclohexanol means
tertiary.
that's cyclo OH. Secondary.
Secondary.
Sorry, that's secondary. Sorry.
If they're giving name of that compound, there's a reason for that.
Oh, it'll be exactly the same.
It would be exactly the same as this. It would be exactly the same as this. We can still use acidified permanganate or acidified dichromate because it's a secondary alcohol. So that it will react, but carboxylic acid, butanoic acid would not react with those strong oxidizing agent. Yes?
It's just literally the same. Just,
Yeah.
When can you not use the acidified potassium permanganate?
What if we-
except for the first and second degree?
Huh? Then you only have a tertiary.
No, so except for the case where you're like comparing first and secondary alcohol,
Mm.
can you use acidified potassium permanganate for every reactions?
I don't get it.
So some has limitations, right? Such as like what is it? The lime water test between the carboxylic acid and alcohol.
What? I'm lost.
He's confused.
I'm lost. You make me confused now. Okay. Lime water test is only testing for the presence of the carbon dioxide gas. And carbon dioxide gas only be produced from acid and carbonate.
But because alcohol and carboxylic acid both have an acid property, like
It could form some carbon dioxide gas.
alcohol, like acidified potassium permanganate, is there like no limitation? Can you use it like every time?
Oh, it has a limitation. It doesn't tell you whether there's a primary or secondary.
Except for that.
Yeah, it also has a limitation that potassium permanganate would react with alkene. This is why I don't use that in the first go. I use the bromine water to test the alkene, eliminate the alkene, and then use the potassium permanganate to test for both alcohol and carboxylic acid.
Would this question be in the HSC?
Kinda, yeah. Too easy. Isn't that easy? You know what the answer is. You know what the method is. You know you kind of memorized it in the prior to the HSC. It's kind of given question. The 3 marks. And I'll be furious if you lose any single mark from that method question. I'll be really furious because it means that you have no chance to get a band 6. That's the fact. The same as like you're getting wrong with the calculating number of moles sometimes in the module 2 before.
So if alkenes and permanganate react, what will be the color change?
Read that what is written. I explained that a few minutes ago. Yes. Yes. Okay. In 10 minutes. We still have more to go. All right. So that's the kind of chemical tests. You okay, Dongyu?
Yeah.
You okay, Dongyu? This is, I told you, this is kind of puzzle pieces, putting like solving a puzzle. That's what I mean. Like you have to think. You need to know every single test. This is why I want you to study. I want you to memorize. I want you to practice here. Why are you so excited? Huh?
I look at drug analysis.
Okay. Okay. All right.
That's gonna be me when I grow up. I'm gonna be a drug analyst.
Oh no. All right. Second method. This is a. I told you that you get the 7-9 marker question from this chapter, and this is one. Yeah.
9 marks.
9 marks. In HSC.
What question?
The whole question is 9 marks.
The whole question? What do you mean by the whole question? Like A, B, C?
No. The whole question.
Wagging, scissoring, rocky.
Okay, show you one. 2022 HSC. 7 marks. The whole question. No part A, no part A, B, C.
Takes 2 pages.
Oh, more than that. You need to write 3 pages. This is what you're going to learn now.
Oh, those are.
Oh, Sheen does in like the trial papers.
Yes, you will get those in 2 weeks.
Yes.
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 And give you about 20 practice questions for these today. All right, let's go for that. So we have a few. Okay, the limitation using the chemical test, it doesn't really like give us good idea about what the chemical is qualitatively. So for example, using the sodium metal for carboxylic acid, it only tests for the functional group. It doesn't tell us that what the carboxylic acid is exact. Okay, so to overcome the limitation of those tests, we use some of the instruments, and you're gonna learn and memorize some parts of the 4 instruments. Something is known as IR spectroscopies. Second is, you don't need to copy this down, it's part of that. IR, and second is the mass spectroscopy. Third is the H. I should start with the carbon NMR, CNMR. And the next one is the HNMR. You need to know 4 of these, and you need to know how to interpret the data. You need to know the function of these machines too. Told you, module. Oh, I'm gonna use some physics here, by the way.
What? Twisting.
Ask Dongyu, we're learning chemistry and physics now. We're doing like atomic models in physics now. We're doing Bohr's model again. Schrodinger's model in physics. I don't know. No. At the end of the science, they actually combine all. So we use
Biology as well? Biology as well?
Yeah, we're doing biology and chemistry later on. You gotta learn about something called the carbon cycle, eutrophications, air pollutions. All right, let's talk about the IR spectroscopy. I will try to make it really easy here. Okay, You don't need to have some physics background, but if you have some physics background, it'll be better for you, to be honest. So, thinking about the bondings. All right, guys, this is how I can represent the bonding. Can you see this? Can you see this? Okay. I have one thing is attached. So basically, I have something light attached at the end here, compared to when that heavy thing is attached here. All right. First of all, depends on the carbon and something is attached. Depends on masses where we're hanging. Of course, they are having a different mass. So if I swing them, you will see that they have a kind of different, like, the wave, or difference of like the frequency, or difference of the vibrations exerted from here. Ouch. Ouch. That hurts.
I swear you always does that. Every lesson.
Okay. Yeah, you can find me the YouTube video say ouch. All right, so what that means is, depends on what you're hanging, depends on what the kind of bonding you have, they will have a different, like, some of the vibration. This is very important. Means that if we have a bonding between, for example, carbon to the carbon and carbon to the oxygen here, the bond strengths would be different. So they have a different bond strength given here. You don't need to understand, you don't need to memorize the form here, but what you need to understand here is, because of different bond strengths, that will make the different vibration when we just shake them.
Do we write it down?
It's written all here. Okay, they have a different kind of vibration. Can you imagine, like, when you're holding something really small and tight, the vibration can be minimized, so that kind of what we get from there is we can get the signals from that vibration here, and that signal is known as the infrared light, infrared EM wave. Okay, or if you have the infrared, and we can't see the infrared in our eyes, so we use something called the infrared spectrometer to capture that signals. So what you actually see from the infrared is, you can see that this is showing some kind of waves of the infrared. All right. Then what we get is, depends on it's given on page 118, depends on bond energy over here. Each of them have a different absorption of the wave numbers, or absorption of the energies there. So greater, you can imagine that the shorter, smaller bond energy, greater the bond energy, would have the greater absorption of the energy too, because they are more rigid, they are more durable to hold that much energy. Does it make sense? Okay, so just remember, as greater the bond strength can hold greater the energy, more tensor, more stronger, so that it would appear to be a greater absorption wave number in your graph. So for the IR spectroscopy, what you get is, you get a graph like this on your page 122. Sorry, they are page 121. Let's look at that here. So for the propanoic acid, what we do is we kind of give some energy to the propanoic acid and make them to be vibrated, make them to be shaken. Now, bonding between carbon and the carbon and double bonded oxygen, compared to bonding with O and H here, they will have a definitely different bond energies. Okay, and then what we can see here is, we can see the very specific shape of that signals in your graph here like this. So as we can see, on the x-axis you have something called the wave number. Simply means that the amount of energy they received. On the y-axis we have a transmittances, means like some of the numbers here. Okay, let's go quickly, let's go really simple here. You don't need to memorize all of this. What you need to memorize here is, you need to know the shape of each of that functional groups. Shape of each of that OH or CO, which is all given on your formula sheet. It's all given over here. Yes, there's a time to use that other part of this formula sheet here. You will get the formula sheet in a second, okay? So if you can find, you have a formula sheet, you will get this kind of, this is actually from the last HSC, you will get this in the HSC. In the second page of your formula sheet, you will see the infrared absorption data. It shows that for each of the bonds, it has a very specific wave numbers given. This is a clue, this is a key that you can use to find that. For example, we have OH at the wave number of 3,200. That's a 3,250 to 3,550 centimeter inverse there. Make sure you show the unit. Yes.
Beautiful machine.
Said. I'll give you in a second. Wait. Okay. You can use that. For the COO here, we have a very specific wave number of the 1680 to 1750 centimeter there. This is kind of location. This is the kind of location that we can find a very specific the functional group or specific bond type in here. Okay. Now, the way we describe the signal here, we can describe the signal as description of signal as kind of broad. It's also given on your page 121 on the top. We can describe the signal as strong, medium, and weak. Depends on the length of these signals. Depends on the width of the signal. We can describe that as broad, very broad, or narrow here like this. So when you're describing this one here, the OH would be strong, and it's actually very, very broad. Now, strong and very broad signals at which distance here? Using this to 3,250, 32, 3,550 centimeter indicate the O and H bond. This is how you can write or interpret the signals given here. Write it down, guys. So we have one strong and very broad at 3,250 to 3,550 centimeter inverse, and that indicates the presence of the OH bond. Yes?
Why is it like OH and CH?
CH is kind of combined. So the reason why we don't pick the CH is in every organic compound, they always have the C and H. Most likely, they always have C and H.
So it's just there for the law.
It's just there. I mean, it's kind of combined with the OH. I show you that in a minute, like a different functional groups too. Okay, what else? We also have the signals here. Another signal is we have a strong and narrow signal at the position would be 1650, 1680 to 1750. I'm using the number given on your data sheet. Yeah.
Do you expect us to memorize numbers?
No. Why would you? Why would you? I mean, for this, no. For this, no. There is something that I will ask you to memorize later. Okay. For this, at this position here, indicate, represent the double bond here. Now, I told you about this is kind of solving a puzzle. We have a bond of the OH. We have carbonyl bonds here. So what would be the functional group having carbonyl, C double oxygen, and OH together? It would be the carboxylic acid. It only be the carboxylic acid having both of the bonds in here.
But what about all the other little ones?
Oh, very good question. All the other little one, this region here, we call this fingerprint regions. You don't need to care about these yet. Yeah, this is actually telling you that, like a fingerprint, giving you your correct identifications. It gives you the what the chemical is, but that's more than year 12 syllabus.
It's like U11?
Yeah, most likely. Now, for this is what we can use. Page 120 gives you some ideas about them too. As we had discussed in here, carboxylic acid would have definitely be forms of this. It's showing you the numbers given over here. Now, in case we have alcohols, alcohol will be showing on that part here. This is something data that you can use. So, which means that if you have an alcohol, I showed you what the alcohol is in the second in here. Page 126, question C, is showing you on alcohol. Now, can you guys see the difference between this shape here? We have a very strong signal, by the way, really strong signal at around the 3000. But compare that to what we have on the page A here. Can you see the difference between the shape of these really broad at 3000 to the one over here? John, what's the difference?
It's very...
The one we have on the top is very broad. It's almost like it's showing like some kind of mountain shape, the reverse of mountain shape. Okay, this is due to, this is a combination of the C and H with the OH kind of combined together. But what we have on here is, it's kind of splitted. So we have the broad shape, and with the CH, this is represent CH, that represents OH. Okay, so that is a shape of the alcohol. Yes, I'm asking you to memorize the shape of different functional groups, because you only get 5 or 6 in your 12 syllabus.
Wait, why?
Unlike,
Separate again?
because that's separated by OH bond and the CH. For the alcohol, they're somehow not giving them, because the difference between alcohol to the carboxylic acid is simply be like this. Okay? All right, and we also have C and double. It is just what it is. It just look like this. It's just like, why you look like you, same as that. Why your height is
Why
that?
did it look like that?
Yeah, I mean, like, it's all DNA structures basically. It's all like this. It's kind of embedded in you. Same in here. They are, because they're forming of this. Because I don't want to go really complicated in here. I just make your job really easy.
Yeah.
It's shapes like this kind of W shape, or kind of like the kind of broken shape, broken mountain shape. That's representing alcohol. That's all you need to remember. All you need to remember. Okay. We can also find the carbon with the oxygen, which is also given on the page there, at around 1052. So for the alcohol part here, 1050 to 1300. So this is kind of telling you 10 to 1300. Yeah, that's kind of the region that telling C and O, which is the bond between oxygen to the carbon here too. Again, but this region here is really complicated. Depends on what carbons we have, depends on how many carbons we have, they can have a really big number differences here. So you don't need to count them. What you need to focus on is these regions. Okay, so let's have a practice of these one here then. Question 1 on that page 123. Let's use that. Let's use that. Use the following infrared spectrum of the unidentified compound to identify the functional group present here. Now, time to have your formula sheet this time now. Yeah, could you pass this? Thank you. Okay, after you having this, let's just describe what we have in here. Show me. What do we have? What kind of signals can we find in here? Can we find in here?
So, CH.
There's a CH, okay, but there are too many CH. What about the clear feature? We have this peak, this peak. So let's describe it. How are you going to describe the peak? It'll be there's a strong and broad, very broad signal or absorption signal at the wave number of the. Now, then use a number given over here. Okay, use a number given over here. You get 3,232, 3,550 centimeter. Make sure you put the units at here. Is representing what?
Oh wait.
No, it's not alcohol. It's the OH, which is an acid.
Wait, what? Isn't it? No, base. Wait, it's alcohol, isn't it? 220, 1500,
No, alcohol, OH. Oh, sorry, acid. Sorry, my bad. Means that's 2,500 to the 3,000 and 3,000. We have a 2 OH. One is about alcohol, one is about acids.
But what about like the other half of the thing?
What other half?
Like you know how the
This
it's
half?
strong and very broad. This
Yeah.
past 3,000.
The left one?
Yeah,
Just-
left part.
Here.
Yeah, like 3,000 to the left. Like
Okay, for this, the trick is, this is why I ask you to memorize those shape. The shape. This is not broken, this shows the whole mountain structure. That's representing OH in acid. That's it. Yeah.
What if that shape was like more further along? Then it wouldn't be an alcohol. Would it?
You won't get that.
Oh, you won't?
You
It's
won't.
impossible to get that.
Impossible. Okay? I'm trying helping you to make your job really easy here. Memorize the shape. The shape, the mountain shape, means it's the OH of the acid. Okay? And then let's confirm that. Well, what else we have? We can find that this signal.
Let's see.
That's a signal. So there's another signal. There's strong and narrow. Kind of medium to narrow.
That's medium.
It could be considered to be a medium. I mean, that could be like, you know, it's kind of relative terms.
C and
Narrow.
right?
Yep, that's represent at where we have 1682, 1750 is indicating
See
the carbonyl. Okay, so combining that, we have carbonyl bonds, carbonyl and OH together. So therefore, the positive therefore, the functional group of the compound, of this compound, is carboxylic acid.
Why do we need to do the like strong, broad, and strong?
We sometimes get the narrow and different thing too. This is how we just can describe that, how they look like.
So it's not like really that. Like obviously you got to.
Yeah, because otherwise we don't know. Like, you know, if you just say that there's a signals, I mean, there could be different signals in the same region here, different region here. So this is more about expression you need to do. Now, this has molecular formula of the C2H4O2. C2H2H4O2. So what would be its name? What would be the carboxylic acid with the 2? It would be the therefore it is ethanoic acid, which is CH3 COOH. Is that a C2H4O2? Yes. So if you're given the molecular formula and if you know the some functional group, you are able to determine what that is. All right. Try the next one. Try the next one.
Wait, so you know when you said you gotta ignore the half of it? You gotta ignore like some part of
You gotta ignore this part here.
Is
this
always
part.
Left, like right side?
Always. You always get the same wave numbers.
Do you look at the very left side? You know, I'm getting confused. 'Cause
Yeah.
like from which part do you
What
start?
can you what can you find in that?
You can find that. You can find alcohol.
You can find the alcohol. Can we?
No, CH1.
Okay, let's describe it. So question 2. I can see the signal here.
I don't get where. You know how you said ignore like the right side.
Yeah, ignore that. Well, if you want to, you can use that some, but we can't ignore it now. Jeremy, what can we see from there? What's that signals? How would you describe the signal?
Strong and narrow signal.
It's a strong and narrow absorption signal at 1620 or 1680 to 1750 is representing what? Yeah, we have carbonyl bond. Yep,
simply using the 3,300 to 3,500.
What can you get from there?
Isn't it like NH?
No. I'll show you what the NH look like. It's not an NH. It's not an NH. NH doesn't look like that. We just see like some peaks there. It only represent carbon with the hydrogen. That's it. That's how they look like. Okay, so we only have one signal, so we can from that. Well, from what we learned, we only can get one thing. If you want to exceed that, there are some signals, narrow and kind of broken signals, 1300, which is this region here. Okay, so we can also say a weak, a strong, and a narrow signal at 1000 to 13 is indicating. It's kind of indicating the carbon with a double bond, carbon with a single bond.
I thought we ignored that side.
Yeah, we can't ignore that. So this can just, you can use, if you can clearly see the signals here. But again, you can ignore that. You can ignore that. But having this, we have a carbonyl. Its molecular form is given as what? C3H6O. Time to solve your puzzle. We have C3H6O when you're on oxygen.
Is that aldehyde?
It could be aldehyde.
Oh,
Could it be ester?
It can't be ketone.
Oh, it can't because.
It can't be ketone. So use, think here. It can't be ketone, but ketone needs to have 2 oxygens. Sorry, the ester needs to have 2 oxygens. So it tells you it's either be aldehyde.
Well, why can't it be? Why can't it have 2 oxygen?
It's given.
Can it be a ketone?
Hmm?
It can't be, right?
It can be ketone
Oh,
too.
it can?
It can. From what we learned.
It's in the middle.
Yeah, it can. So we don't know. It's either these and that. So this is 2 possible. There's a 2 possible like a functional group we can have in here.
So the
But what about the bottom one? It says that there's a CO. Doesn't that like kind of show that it might be an ester?
I think the purpose of that is actually like
Ignore it.
both
you
of
just
them-
ignore it. Yeah,
both of
just
them have
yeah,
COs.
it just ignore it because you have a carbonyl here. Just kind of ignore that part T, if that makes you confused. So from that molecular formula, from the information here, it must have the carbonyl, and the only possible thing is aldehyde and ketone too. And then because this is a limitation of the IR again too, it doesn't tell you sometimes like exact functional group what we learned yet. It's give you brief ideas. So this is why we need to have a 4 different tests or some of the chemical tests to confirm that it's functional group and find what it is later. Okay. Next one. Oh, by the way, the questions that you would get is something like this. I show you that again, the HSC last year. Chemistry. You're given the 4 different parties. So let's quickly have a look at this, like something look like the thing. Ignore the fingerprint region even given here. This is from the last year. See that? This is what I mean. You're gonna ignore that. But the question is this: the following spectra is obtained from the unknown organic compound. You're given this mass spectrum, infrared spectrum, proton NMR, carbon NMR, and you just need to find out what that is.
Oh my god.
Based on all of them.
Yeah. You got to use every single spectrum, 7 marks by the way, to find out what that is. They won't even tell you about the test. That's all you get. 4 graphs. From the 4 graphs, you need to know what that is.
They all indicate one.
What that it means, you need to know its exact structure. Number of the carbons, hydrogens, functional groups.
They didn't tell you like the C2 like H.
Never, did they?
Well, some people might actually like it.
Oh, you will like it at the end. I'll make you like it.
What do you mean by that?
I'll make you like it. Yeah. Oh yeah, Brandon, and they loved it.
You need to convince yourself that you like it, so you study it more.
No. You will like it because this is the actually the question that you can get a full mark.
Oh, it's like an induction question.
It's like if you know guys. This is what I mean by guys. Make sure you practice every week. If you miss one lesson, if you miss 1 week, it will drag you forever. A minute. Study this week. Study this week. Very important. If you miss that, you won't have a chance. But this is why I'm giving you a shortcut. Even the HCC asks you, hey guys, ignore that. Ignore the sections. The only information you can get is this section over here. Let's have a look at the next one then. Identify the type of bonds causing the major absorption band above the fingerprint region, above the 1400 there is the following spectra here. So, what we see is, we see the very broad with the strong signal here. Representing what? This is OH in acid. Very good. Now we see this very narrow but strong at the 17, like 100, like around that region, which represent, see the what? That's it. That's what? Carboxylic acid again too. So you only get a certain type of those, guys. You only get a certain type. And I make it your job really easy here. Just memorize the pattern, memorize the shape. This one here, now we get something in here. B, can you have a look at the B? This time, so I got to write this here for you, the functional groups. For the carboxylic acid, what you have to have is, you need to get the very strong, I just copy that down, and the very strong, broad and strong at the 3000 at around, let's use the number here again, 2500 to 3000. That's representing the C, O, and H and acid. Guys, this will be like your shortcut. This is kind of your fast track you can use. We also have the narrow and strong signal at the 1680 to 1750. That represents the carbonyl here.
You even have to like write a full sentence.
You do.
I,
Oh, you try it right in the dot points. You will get them 0 mark for that.
Really?
oh.
Yeah. Okay, that's how we can identify one. For the aldehyde, let's go through the aldehyde again too. Aldehyde and the ketone from the functional group that we learned. Okay. For this one here, what we can see there is, we will see the narrow and the strong signal at 1680 to 1750, and they're over here. That's representing the carbonyl given here from the functional group we learned so far. Okay, everyone good up to here for the functional group? That's all we can get. I mean, we can't get other information from here. There's a limitation here. Now for the ester, then esters. For the esters, we'll have the same narrow and the strong signal at 1680 to 1750. That's giving you carbonyl. You also have, it's most likely kind of narrow shape, strong to the moderate or medium, I should say medium, signal at the 13,000 to 13. That's representing the carbon with the oxygen here again too.
Or wouldn't that be at the fingerprint region?
Yes, this is why if you don't have that, you don't have to worry about this one here. The most definite one will be the carbonyl given here again too. All right, next one, alcohol. Alcohol will have the, unlike the carboxylic acid, it will have kind of W shape. You kind of have the broad but strong. At the same, in here, 3,230 to 3,550 given here. And the shape will look like this. Something given here, like a broken mountain here. kind of slightly shifted from some sort of the, what do you call, the W shape. That's representing the O and H in alcohol. Okay, yes, we have the C and O, but you can ignore that region here. Then lastly, for 2 amines with NH. Remember this? See, NH2 attached. This is kind of strong in here. You will see sometimes be medium, not that strong, or some could be strong. It depends. To strong sometimes. But the important feature of the amine is the location is at the 3,300, but you will see the kind of tooth shape
Which shape?
like this, or W shape.
That's upwards.
No, that's the difference of W shape. I show you what the difference between W shape and the tooth shape today. Tooth is a kind of pointy tooth shape. And
Is it like a B?
that's B, yes. That's what I mean by tooth-like shape.
Like a vampire.
Like a vampire, like a tooth, like a kind of pointy tooth shape. Now, alcohol, Ian, alcohol, the W shape would be like this.
Ah.
Can you see the difference here? Can you see the tooth shape given over here?
That's amine.
That's amine. That means that there's a nitrogen given in here. This is why I ask you just memorize the shape. Get familiarized with those shape. Okay, so you have that and that kind of tooth-like a shape. Means that at around 3,030 to 3,500, or use a number given that's around the 3,000 there. Okay, 550, 500. That's amine, and then H. Yes.
How is B get amine?
B.
Yeah, so you said B is amine.
No. B is not the amines. It's amide.
Huh?
Now, let's see. Amide then. How are you going to identify amide? Amide means, remember this, we have a carbonyl with the NH2. That's amide. So you got to get the narrow and strong at that. Carbonyl represent carbonyls. So you get the narrow and the strong at 1680 to 1750. That's one. Second, you would have the medium to tooth-like shape or W-shaped. Just use a W-shaped, guys. Tooth-like is like not an official term. This is my term I use. W-shape at around 3,500, 300 to 3,500. So let's use this. Let's have a look at the B then. Jeremy, can we see the really long, strong signals at the 1700 there?
Yeah.
That represent what?
C double O. I see on it.
That's a C with a double R. Carbonyls represented here. Does it make sense? Okay. Now we also can see this shape here, tooth-like a shape, at the region of 3,000 today. That represent N and H. Combining these together, this is amide.
Ah.
Okay.
But that one's at in between like 2,600 to 3.
Around 3,000 here. So we take the whole thing, this part, up to there. Yeah. So this just gives you the approximate numbers there. All right. Next one. C. What we see there is there any, okay, started with the carbonyl. It doesn't have any carbonyl, isn't it? It doesn't have a carbonyl, but it has the broad, yeah, it just shows the OH straight away. Just memorize the shape. It makes your job really easy. Next one. Oh, what about this one?
That's amine.
It could be the amine. We have, this is a really strong CH. And that's kind of representing, it's kind of vague. It could be the C double O, and that could be the NH. So amide here again. You kind of get it? Kind of get it? Okay, try next one then. What about the functional group of this page 127? Carboxylic acid? Possibly. This is kind of vague. No, it's given as here, ester. It's given. So as long as you're given the functional group of ester, think about the ester shape. Ester would be carbonyl with the CO over here. Now what you have to focus for is you need to find this one. This is the carbonyls at 1700 to 1800, around that. Okay? Now, depends on what you have. Yes, I told you to ignore that, but if you can see like clear, really clear like a signal there, which is this. Okay, that represents carbon with the oxygen. You can describe it. See that narrow, strong, medium at the 1,000 to 3,000. That's what I mean. That's the really strong signal here, which is representing what? The ester, methyl methanoate from here. What about this one? That's just simply representing C and H, the carbon with the hydrogens here. Okay, you can talk about it if you would like to, but that's not really identifying the ester. What the identified ester is this one, carbonyl and CO. Try the next one then. IR spectrums are unknown substances shown below. Alright, identify the functional group present in the unknown sample and determine the structure and the substance given it has 3 carbons. And I have a present for you. Amide? Amide or amines? Why? Why?
Because they have the amino NH3 from
Yeah.
strong and W shape.
Yeah. W shape or tooth-like shape. Good.
Like 1680 to 1750.
Mm-hmm.
There's like a narrow strong.
Narrow,
So
strong.
you get CO.
Yeah. C-double-O, which is carbonyls.
But it says to identify 3. What can you do for the third one?
Unknown sample and determine structure and the substance given it has 3 carbons. Hmm? What do you mean?
It says 3
What's that
functional,
amide?
3 functional groups.
Where did it say so? No, it didn't say the 3 functional groups. It said 3 carbons.
Very good one, isn't it? Wait.
Alcohol is like no alcohol. Guys, just memorize it. Alcohol look like this. Alcohol look like this. This is alcohol. Massive, yes. Kind of 2 tooth. Okay. Amide or any NH would be like a tooth, pointy shape.
Then why is that one so low?
Hmm?
Why is that one so like strong? The amide.
Don't ask me that. Again, let's go easy way because I need to explain about like how they actually structured and things like that too. It's get really complicated.
You don't have to know that, right?
No.
So amines is just more sharp.
Amide is more sharp and pointy and the kind of W tooth-like a shape. Yes.
If alcohol is like you need a little squid like a
No. Just this is alcohol. Just don't think about the shape. This is just alcohol shape. Just think that this is alcohol shape.
What's the difference?
Huh?
What's the difference?
You tell me.
Is it because it has a longer divot inside, longer split?
You can see the split. Yes, you can definitely see a split. A more kind
So
of
if
clear.
it's a bigger split, it's alcohol.
Yes.
If it's like a tiny little, like
Pointy.
if you go back to get that one, that's a.
Alright.
Fun times.
It's not bad, isn't it? But just so easy to forget that.
Wait, so
Yeah, like
do
every.
you look at this first, the numbers? So I look at the
No,
numbers.
the numbers. I'm not using numbers in the formula sheet to get the exact numbers. Write it down. You just need to identify the shape. Can you pass this around? This is from the NASA. You have A to Z, the samples. All right, guys. For these, you're all given from the A to Z. A to Z. I think, yeah, seriously meaning A to Z. You'll get all the here. So I show you one. For the some of the groups here, you get the those here. So I show you what I mean by the butanol and butanol here. 동률. Sample M. I go really quickly on this. From the sample J here, okay, let's compare. Have a look at the board. So from sample J, just look at the board here. Guys, just look at the board. 동률, look at the board. Okay, just have a think. J, K, L, M, N, O, P. Can you see some common features?
Yes.
Yeah. So all of this, except the one here, J, L, M, N, O. What are they?
Alcohol.
They're alcohol. See, I'm making your job really easy here. This is how you do it. You just need to describe them. Use your formula sheet. All right, let's go back. Let's see some other things here. We have U, V, W, X. There's A minus or A minus. Depends what we have.
Bro, what the hell?
See that?
What's that one?
That's A minus.
Could be A minus.
What's
Yeah.
that time?
Ooh, this is not A minus or A minus.
It's not A-minus.
Isn't that a tooth?
That's a tooth. That's not like a tooth.
Is that Esther?
Hmm?
Is it Esther?
Was it Esther? You have the answer.
Is it Esther?
T,
Is it Esther?
T, T was pentamone or keton. Yeah. So this is more, again, we don't know like whether that'll be aldehyde ketone, but can you see like so? Yeah, let's check all the O's, and we have amide, and that too. Can you see like there are differences there? Can you see like the clear features? Let's have a look at the carboxylic acid. Do we have a carboxylic acid? G is a carboxylic acid. Can you see the carboxylic acid feature there? Yeah. Can you see the feature? Can we find? Like, let's go through that. Can we find any carbox? This is carboxylic acid too.
There's alcohol there?
There's alcohol there. There's broad, very broad features there too.
Which one's alcohol, sorry?
Alcohol,
Oh, I mean...
alcohol. Ketone maybe. Alcohol.
In the carboxylic acid.
Yeah. Yeah.
The more you practice,
Yeah. I mean, like this is the easiest way to learn the IR. Now, I want you to see the difference in here. Can you see the sample A now? Sample A and sample B. Let's compare to the B to C. Okay, A, B, and C and D. I want you to look at the this 3000s, that section here. This is the kind of hint. A and B has a kind of similar structure. Can you see? There's not much difference, as we can see. But C and D has some features given on there. Can you see that? Okay. Tell me, what's the difference between sample C to B?
sample C has a lot of fingerprint.
Like, let's have a look at this region only. That region.
Um,
Sample B and C.
Sample C has a split.
Kind of split. Okay, what about sample D? We have a split here too. Sample A and B did not have a split.
What are the little spike in the very...
Here,
in the very bottom B? Like A and B, right?
A and B. Well, what about it?
What is that very tiny...
Don't worry about it. Okay? Don't worry about it. I just wanted to point it here. Split, not split. Split, not split. This is alkane.
Okay.
This is alkene.
So is it not
Oh,
broad enough to become
what
an
the
alcohol?
frick? Do we need to know if it's alkene or alkane?
You might need to know that, yeah. Guys, this is from NASA. The sole sample question from NASA.
But then the ester looks like a alkene then, because there's like a little split in there.
But does it have the carbonyls?
Oh, for real.
Yeah.
For real, for real.
Yeah. See?
Can you explain it one more time?
What? About what?
Alkene.
You see the difference? Sample C,
Is it split?
sample B, not splitted,
Yeah.
splitted, splitted, not splitted, splitted, not splitted, alkane, alkene. Yep, go to toilet.
Is it split?
The next instrument is known as the mass spectrum. So M and Z, again copy that. M and Z stands for the charge to mass ratio. It's basically something here. So for the mass spectrum, guys, you need to know how the machines are actually functioning as well too. Yes, you need to memorize the function of the machine. Okay, for the functions, the way you can memorize this function is like this. You can memorize a VIA via DD. Via DD. Just memorize via DD. It would be something. Okay, V stands for, it's given over here, it stands for the vaporization. I stands for the ionization. A stands for the acceleration. D stands for the deflection. And D stands for the detection. So via DD is how you can memorize this. Viad DD. Viad. Or via DD. VIADD. DD. DD.
Can't you say David?
Oh!
David.
Oh.
Deflection, acceleration,
revolutionary.
vaporization, ionization,
Whoa.
detection.
Wow!
David.
David!
David.
Wow, sounds like you.
But that
Well, I
confused
need to
you.
be promoted. I need to be promoted. Teacher, immediately.
That is
Okay.
easy. Now I'm gonna remember.
Yeah, now David. David. The mass spectrum,
And
David.
then look, I can do it. Deflection, acceleration.
Oh,
But what about the- okay,
vaporization,
okay.
Ionization,
I get it, but don't get confused with the order.
detection.
Oh, is that order?
Yeah, or the order matter.
Alright,
The second-
violated.
Oh, okay,
Yeah,
it's fine,
order
fine.
is important. All right, vaporization. Basically, you make this. Okay, what you do is you're putting something chemical like organic compounds, and you basically heat it up, giving some heat. So what they do is it making to be like excited state, making to the gaseous state. This is called a vaporization. So making this called making into some gaseous state by heating up. Okay, those heating is actually using some heat or something to use the electrical power. Now, next part, ionization use. Okay, well, once you get, so assume that we have carboxylic acid here again too. I showed that one carboxylic acid. We have carboxylic acid with the OH and CH3. So it's showing all the carbons and hydrogen bonds. Here like this too. Once this is get vaporized, you get ready to get excited, means that, you know, thinking about like, you know, when we're melting something, the reason why we melt something is we try to make it to connect to something else too. So we kind of give a heat, make it to be more malleable, more ready to react. Then what you do is you actually shoot on electrons. The electrons are shooted on that structure here. The ionization then happens because think about the property of the electron. Electrons are something is a negative. You're basically shooting machine gun of those electrons. Yes, machine gun is like a really like you put shooting all the many electrons to this structure here. Then what happened is electron is something is negatively charged. We have to think about in here something is partially positive, partially negative. Carbon with the oxygen is known as dipole here. The carbon would be more like a partially positive, and this side would be partially negative. Same in here, partially negative and partially positive. Now, because electrons is something negative here, yep, it can break a bond between carbon and oxygen here like that. And bond between these two are so strong. So the rule is the electron only breaks. No, only break electron when you break the carbon and carbon bonds. Okay, even though we have carbon and double bond, the bonding, yes, it can be broken. So the only way we can break the bond here is you can break bond between carbon and oxygen, which is kind of weak, carbon to oxygen as well, and this one in here. Then what they do is this is kind of divided into a piece of this. We can get the piece of that, the carbon with the O, with the OH is kind of detached. Okay, due to the broken bond, we'll be breaking this one over here, and we get the leave of the carbon with the CH3. Okay, that's known as the ionization, using the electron. That's how we can ionize them. Now what happened is, after they've broken down the bonds, the whole thing gets positively charged. And that's super important. We make this unpolar, non-polar, the compound to be positively charged, as we can see here. Now, what we can see from there is the mass of these two are different. John, what's the mass of the CH3?
Pretty light.
Which is?
Oh, like molar mass?
Yeah.
12.1001 plus
15.
So roughly 15 of the mass here. What about this one?
So, much more heavier.
It's heavier. 16, 16, 32, 40, 49? 49? 49, yeah, 49 here. Now, how to think about here. We have I say the charge to mass ratio. We got to divide that with the charge of 1 plus in here.
45.
So, no, 16, 16, 12, yeah, 45. Who said 49?
Who said 49, bro? Jeremy, bro.
Who said 49?
Jeremy saw it.
Who said 49? Yeah? Yeah? Chongmin? Alright, guys, think about here. We have something that have, okay, we have something that heavy is something positively charged. Something heavy like light and positively charged in here. I'm using a little bit of physics here. This gets accelerated by using something known as electric field. So they get accelerated now, used to some really strong electrodes. Now, after they get accelerated, they're ready to move. They get deflected. So they're shooted over here to get accelerated using the electromagnet. That's known as B field. Don't you remember this? Charged particle in the B field making what? Circular motions. Depends on the mass, they will have a different trajectory. So heavier the mass, will move further, lighter the mass goes. These two will have different trajectories. Okay. Now, what we do is after they get combined here, we collect at the end for detection. That's using the computerized system. And we don't really count that individually. We count like making the sum here. Yes, you need to memorize basically all that in here. Word by words, sentence by sentences.
Oh, jeez.
I'm not kidding. You need to memorize them because we had the questions in trials and HSC before.
Is it like the method?
Yeah. I mean, word by word. You do not skip anything in here, Jongyul. Don't make your own summary of that. You will lose mark for every single summarized point. Just memorize word by word. I'm just giving you a shortcut. Don't think. Just memorize it. Okay, but this via DD will help you the guideline of that too. Just need to just write it down, whatever the method is. Because truly, we actually had a question like describe the function of the mass spectrometry, like I had the machine. We actually had a question, 3 marks question. Everyone hated it.
Just describing it.
This.
3 mark only.
Yeah,
That doesn't seem that
like 3 marks. If you memorized that.
More like
So
3
is
marks.
do we have to know the name of the exact equipment?
Electron gun.
Yeah, we have to know
You
like
do need to know everything.
ion repeller, electron tap, electromagnet.
Yeah.
Vaporize.
It's too, the
Does
words are
it
too,
say here?
too big for me.
Yeah, it does. From the electron gun.
Now,
Ion repeller.
yes, and everything is given here. Now, what's important there is after we collect all the samples, after we collect all the fragments, so we call these the fragment ions. And all these fragment ions, depends on the mass, they will make a different deflection. Therefore, we can only, depends on the deflections. The amount of sample we can collect, it will be different. The amount of the sample we can detect would be different at the end stage. So what we given here is then, after that,
Oh, can you take a picture?
of this, yeah.
So what's the video?
No, the picture's so easy, John.
Yeah, right. I thought you can airdrop it to your iPad and everything. Yeah.
Okay, page 131 shows that what I showed in here for these exact thing in here. So after it gets shooted by the electrons, there could be a bond broken between this carbon to the CH3 to COH, losing the N or the C to there. So leaving some fragments of the CH3CO plus, of that making the CH2CO plus, or fragment of CH3 plus given here, or the fragment of that too. Now, in your mass spectrometric in the formula, the graph, you are able to find that on the M to Z, which is on your x-axis. That M to Z here is simply giving you the mass, molecular mass, I should say, molecular mass of the fragment. Okay, now depends on the deflection. The amount we can detect quite differently here. So what we do is we choose something that the most abundant. So in that case, CH3CO is the most abundant.
What's that
Means the most, we get the lots of those. Saying, I give you some example here. Let's say we have like thousands of them. We detect thousands of this. Okay, what we do is, because we can't really use the quantitative number here, we make the 1,000 to be like 100% of the whole thing. And then the rest would be just relative value. For example, COH, if we have like a 900, instead of around the 900, because we made the 1,000 to be 100% for everything, 900 will now becomes 90% for the intensity values. This is called the relative intensity. Relative means we got relative values here. Then if we have 100, if you have 100, it only shows the 10%, which will be there shown as the length. Yes, this is something you've done in the module 1.
What? Physics, right?
No, chemistry.
Oh, what?
You did about relative isotopic mass.
What? Did we? Hey, Jeremy, did we? You're nodding your head. Oh no.
Yeah, I thought he knew.
Joe's just nodding his head because for the face for a second.
Don't worry. Okay, you don't need to come back to year 11 to study this again. Just study now. Okay, so the most abundant, like the one, the most what we have is known as the this. Therefore, we call that becomes 100% because we have most of it.
Becomes 100%.
Yes, 43, 100%. As we can see that 100.
That becomes yeah, okay.
That's 100. Based on that number, we compare the quantitatively, so they relative values. We call this 100% peak is our base peak. Due to that reason, we call the base peak.
Do you know why that? Why 43 is? They're not 4%.
Yeah, why is that?
I don't know.
Thinking about what makes them, yeah, what's so funny?
You asked the question, and then you asked it back to him.
Oh, I was just thinking, oh, okay. Oh. It's my job to ask you questions sometimes. All right. The reason why we have the longer, like the greater number of the iron, this can be in your test. The greater number of iron means that we have more number of that present here. Means the greater chance we have more of the CH3CO is actually this part over here. So that look like COO with the CH3 here. That's the CH3 and CO plus. Okay. Do you remember what I said about when this is shooted by the electrons? Okay, there's a structure from here. When this is gets shooted by electrons here. Bye. Okay. The electrons get like a okay. Electrons will most likely attack where, Jongmin?
Polar bonds.
Polar bonds, which is polar here. What are the polar? So in between carbon and carbon, yeah, with the central carbon it's partially positive, so it will most likely attack the bond between carbon and oxygen here. Because the partial positive charge of carbon is almost like attracting that, making the good targeting. It'll be good targeting here. In other words, to break bond between here, CH3 and C, it won't be that much. It won't be that much compared to the bond between this here. Okay? So you can remember that as electrons will targeting those carbon, which is partially positive or molar positive. Due to that reason, there are more chance of the breaking bond between carbon and oxygen. Therefore, greater number of this CH3CO, which is what product of the breaking this bond in here. This could be present due to that reason.
So, is there any like?
Wait, what?
So what about the 45 molar mass?
What the frick?
45.
The molar mass.
COH.
Does molar mass really contribute to?
Yeah. So, okay, let's have a look at that again. The carbon, I showed it again. Carbon with double bond oxygen, O and H, and CH3. Now, the central carbon here is a partially positive, isn't it? Which means when it gets heated by the electrons, like attacked by the electrons, these electrons can attack partially. This is good targeting. We're targeting this carbon because it's partially positive and from negative. The only targeting point then, if that's attacked by this electron, it would be bond between carbon. This one can be broken. Or this can be broken too. Double bond is not broken. It's only kind of working for carbon with the carbon and carbon with the oxygen. That's too strong basically. What happened? Okay, I'll give you a reason for that too if you want me to. What happened between that is that's a partially negative. It's kind of repelling. It's kind of like a shielding effect, kind of repelling the negative charge, making a good barrier so that double bond is kind of safe. However, partially positive is not that safe. So more likely, the electrons will be attacking that partially positive carbons. Only two possibilities then. It's either be carbon to the oxygen, carbon to the carbon. And this is kind of shown in here. Base peak of 43 is resulting by breaking this bond. We have more of these appeared due to that. Another peak, the second best, the highest peak, 45, COOH. Where's the COOH? This part. There's a COOH.
So what is that big number like? What does 43 represent?
43 means the mass number of the COOH.
Why does it matter?
Hmm?
The molar mass?
It's a molar mass.
Does it matter though?
What
Is it like the reason that why we have to know the molar mass?
Oh yeah, you have to know some differences here. It's more physics.
What intensity is it showing?
Iron equals.
Don't worry about this one here.
Is that Fa?
No.
Iron. Iron equals
Those who want to investigate it, study that.
FC.
You've done some physics.
I hate physics.
Me too, though.
Yeah. This is why don't bring me here. Guys, don't bring me here to explain about physics. I just want to stick in here and try my best to explain this as simple as possible. I tell you one question okay, I spoil it. One question that you will get in your trial practice. You will be asked to given a compound, and you will be asked to draw a mass spectrum graph.
Wow.
But when we look at the mass spectrum graph, what are we meant to look at? Like, what do we take in?
Oh, good.
Like, 'cause
You
the
have
other ones-
one. You need to look at what possible fragments can be formed.
It's just all of the stuff on
All of those in here are the fragments. Two, you need to determine which one has a higher percentage will be formed. Means COH or CH3CO, it has the more greater percentage could be formed by the attack of the electrons. The more abundant compared to the others here. That's a 2. 3, the last peak over here, CH3COOH, is something we know as a molecular ion peak, which means that the whole thing here somehow gets positively charged by the attack of the electron too. And this is the very important information because that 60 tells you that molar mass of the compound. Yes?
How do you make CH2CO plus?
CH2CO plus, which is this, they can lose the hydrogen further after get attacked by that. But the chances are really low. We only have this many here.
Can we lose more?
Yeah, you can. But we don't, maybe, but we don't really detect them here.
Just by itself?
Can you get O?
No, by attacked by the electrons
Oh.
too.
Is it possible for O to be by itself? Like at all?
No.
16.
Okay, now important information one. You get to, from the base peak of the mass spectrum here, you can determine its possible structure. Yeah, because the most abundant peak, base peak, means that they most likely get attacked by the electron. Due to what? Partial positive of the carbons in. Okay. Okay. Second, the second information you can get from the mass spectrum is from that molecular ion peak, you can determine its molar mass of the whole compound. The molecular ion means the whole things get positively charged in here.
So if it gets attacked by the electron.
Yeah, the whole things somehow whole things get positively charged. So the information you can get, this is the important thing, guys. The information you can get from that is the very last peak on the right hand side is representing what? Its molar mass.
I see.
You see?
Yeah.
You're right, John? Okay. Now, why we need to know the,
How do you know the height just by looking at the equation?
you know, by looking at the structure here, again,
I'll know that O11C and CH3 will have the highest.
greater chance we have this, that,
Like that.
yeah.
Actually, that's the second rate.
Well, like, you know, for now, well, you don't really know, like, you know, why that has a higher peak, higher that, or why could that be a base peak with that too. That's related to physics. Greater the mass in the centripetal force is kind of different.
But when we draw it, how are you meant to set the ratios?
Hmm?
When you
I'm
draw-
saying, don't worry about it.
But you just said like we might get a.
Yes, but in that case, you gotta determine like which could be the base peak. You can kind of take a guess. It's either that or that. It's either this or this is the base peak. You just need to show the base peaks. What could be the base peak? Ratio could be a little bit matter too. It's as long as you show the good ratio values, you should get a mark because it's not exact. You're estimating the mass spectrum here. Okay, to understand the point, after you get the molar mass, if you know the functional group, okay, IR, John, what was the information we can get from the IR?
IR.
Functional group.
IR.
Yeah, what's the information we can get from the IR?
Ah, like the graph. Isn't that the graph? IR's like. Wait.
He's still going.
No, it's done.
I need to tell like the functional group.
Yeah, we can tell the functional group.
Oh.
John, what's then information we can get from the mass spectrum?
The graph.
That's the graph.
Molar mass.
We can get the molar mass. Now, you have a functional group, you have a molar mass. You have a functional group, you have a molar mass. Can we determine its molecular formula?
Yes.
We can.
Wait, can we?
Yeah, and then you need to memorize some points over here. Told you, this is got to be really content heavy.
More than
Do we
what's
learn
in-
up to isotope today?
Hmm?
Are we going through isotope?
Oh, we're gonna finish everything.
Three?
What?
2 to 3.
Yeah,
Can I go to toilet?
quick. Okay, all right, let's have a look at the 3.3 then. From the example 2, the peaks at 15 and 45 are the two possible fragments that are possible when the bonds between the carbon breaks. Explain why the peaks are the different sizes here. Okay. No, let's go for the given value here. Page 133, question 2, please, guys. Question 2. The mass spectrum of the unbranched alkane has a molecular ion peak. You've done?
It's penalty.
Oh, okay. The ion peak of the M and Z ratio 86. Determine the molecular formula of the alkanes and given its name. So it's given the mass to molecular ion peak. Mass to Z, charge to mass ratio is given as 86. From here, we can get the molar mass of the compound is known as 86 gram per mole. This is how we can start your question here. And this is known as alkane. So alkane has the formula of the CnH2n plus 2. That's alkane general formula. Unbranched means that it doesn't have any methyl. So this is kind of we can use here. So how do you find that N? You can use 86 molar mass of the alkane can be found by 12 times N, which is 12 is the carbon's mass number, plus that 2, H2N plus 2. So that's 2N plus 2 of the hydrogen.
Would it be 12.01 or doesn't matter?
Oh yeah, we kind of ignore that decimal points because we have some whole number given over here. You get the 14N plus 2, so N is therefore 84 divided by 14, get 6. Then it must be the C6H14, which is what? Hexane. That's how we can use it.
And just from the molar mass.
That's
And-
inspiring.
Just from the molar mass, and if we know what the functional group from the IR, we can find it. Yep. So this is why you're given 4 graphs. For each of the graphs in the HSC that represent a different information. And then your task is you need to identify them individually. But guys, how do you feel about IR now? Dealing with the IR, it's pretty good. You get frightened by looking at the IR in the first hand. But by looking at the structure, by looking at the shape, it's pretty easy. Just like in here, you just need to learn what the graph is represent, what information you can get from each of the graphs. That's all you need to study. Plus some functions of the machines too.
So for the mass spectrum, you only care about the molar mass. That's given.
Molar mass is the prime information we can get. But the secondary information we can get is by looking at the base peak, we can determine it's a possible structure.
So when you get the 3 stuff, right? The IR spectrum, you find the functional group.
Most likely you use to find
Mass
functional
spectrum,
group.
You find the molar mass or the
It's more likely molar mass given that too, yeah. Or we can relate that. If you have from the IR, say like carboxylic acid, John, okay, okay, you have a carboxylic acid from the IR. Use the information to match to the mass spectrum. Why are you bench pressing now? All right. Question 3. Try the question 3 then, please. Oh, nice. Molar mass is given as then 58 gram per mole. So 58 for the alkane with 12N plus 2N plus 2. So N, yeah, that's 4. Therefore, it's a butane. Very good. Yep. What's the molar mass of the carbon? Thank you. Now, depends on what you have. So I show you the page 135 here. This example 3. It shows that the structure of the CH3 and the Cl. This is a mass spectrum of that. Okay, let's have a look at here. First of all, by looking at that, we can determine it's a molar mass of the whole thing. First, it is one thing here. But carbon and chloride is having some polar covalent bonding, so there's a chance the bonds can be broken. The bonds can be broken between that here. Or the whole thing's got to be positively charged in here again too. So by looking at the very last peak over here, we have 2 peaks, and we have certain fragments peaks over here. Can you see that in your, the example 3? Now, the 2 peaks at the last is due to that as chloride has isotopes of the chlorine 35 and chlorine 37. Do you remember what the isotope is?
Yeah.
What's isotopes?
Valence shows.
No. Isotope means same proton number, atomic number, with a different mass number, which means they have a different number of the neutrons. So chlorine 35 and chlorine 37 means they have a different number of neutrons. By the same time, they have the same proton number here. And it's kind of naturally happening. So when we collected some of the sample of the chlorines, some of the percentage would be chlorine 35, some percent would be 37. So it depends on that, depends on the isotopic types, we can have a kind of different peaks as is given over here. Does it make sense? Okay, so that's really popular in the that's known as isotope effect, and that's really popular within oxygen, chlorine, bromine, even carbon and hydrogen is given here. So hydrogen has an isotope of H1 and H2. Means that there could be a like little percentage of the hydrogen having neutrons together. Now, carbon can also have some percentage of the carbon-13, which is rare, really rare, but 1%, about 1% of the whole carbon is actually carbon-13. Oxygen has 0.2%, so it's kind of lower chance. Now, for the chlorine, this is very important. Chlorine has 75.8% of the carbon chlorine 35, 24.2% of the chlorine 37. Which means when you're showing on the mass spectrums, some percentage of the carbon isotope will be shown, as we can see from the example 3. Bromine is actually worse. We have a 50% of the bromine 79 and bromine 81, which means your last molecular peak for the bromines will be almost like the same. You have two equal lines like that too, for the bromine parts only. Chlorine parts, we're seeing that 75.8 for the longer peak and shorter peak, as we can see from the example 3 here.
What's it? Like the chlorine itself, just
Mm?
in the middle.
Yeah, it's the chlorine itself.
75 and
75 and 25? 75 and 25, what do you mean?
35. The abundance.
Comparing that, yeah, it will follow some of that. It doesn't really like follow the even there, it's not a really 25 of that too. Okay, or compare that. There's actually 1/3, 1, 2, 3, 3 times bigger. You can use that value here. Okay, then Jongmin, why do we have these fragments? These fragments, the small fragments. What's the reason for we have a really small fragments there? What are those?
More split up.
What do you mean the more numbers? We have more fragments. But this means that this has a greater, compared to CH3,
Hydrogen's disappeared.
oh no,
Like the
oh it's not disappeared, but getting
Just like
close.
break off, got break off.
Oh, not the broken up yet. No, those small lines, small like short lines, are representing what? It's due to what? Have a look at their difference here. It's only be 1 or 2. There's one difference here for the mass number. This is due to,
Hydrogen.
yes, hydrogen and carbon's isotopes.
Hydrogen.
Hydrogen have isotope hydrogen 1, hydrogen 2. Carbon and carbon 12 and carbon 13. So some of them must have that carbon 13 or even the hydrogen 1 in here too. That's due to that. It will have a different small short lines given as that too.
What's the number?
What number?
How many lines you have?
This number?
Like the number of lines. The small line.
Yeah. I mean, the small line doesn't really matter. Like, you can have the various numbers. But the big lines here, let's count. Let's see that whether it's right or wrong. We have a CH3 with the Cl over here. Okay, just have a look at this. Just have a look at this. What would be the possible fragments of these CH3Cl chloromethane when this get attacked by the electrons? There's a chance that the bond between carbon and chloride can be broken, so it can be broken here.
or everything.
So it will be, we're leaving one CH3, you're leaving Cl. But Cl, chloride has 2 isotopes. You remember that? It either shows 35, chlorine 37. That's 3 fragments first. What else? We can have a whole things get fragmentized. So we can have CH3Cl, but this case we can have Cl that is a 35, CH3Cl is a 37. So how many peaks? 1, 2, 3, 4, 5 peaks.
What about
Hydrogen?
hydrogen? You look at the long ones.
Yeah, I'm just looking at the long one here. So let's check how many peaks, the long peaks we have. We have 1, 2, 3, 4, 5, matching to this information here. Okay, for that, and then here, we don't know whether which could be the base peak. This is limited up in the year 12 levels, but as long as you get the number of the big peaks right, you surely get the full mark for that. Does it make sense to all guys? John, you're about to fall asleep. Okay, what about this one? Page 136.
We do it.
Yes, please. Could you pass that one? Thank you. All right, what is the molar mass of the compound? How to get the molar mass again? We can get the molar mass by looking at the very last thing, the peak on the right-hand side. So the peak molar mass would be somewhere in between 114 gram per mole. B, what is the mass M and Z value for the base peak? What's the base peak? Base peak is the tallest, highest, which is this one here. Okay, so mass to Z, following this, that's giving you about 43. Is the mass to charge to mass ratio of the base peak.
What's the unit?
It's a ratio. Yeah. Don't worry, you will learn that in Thomson's experiment in 2 weeks in physics. Okay. See, what is the name of the alkane represented? So we have an alkane with a molar mass of 114 gram per mole.
Octane.
Oh, octane. I like it. C8,
There's no octane. Yeah, there's
I got
a-
9.
I love octane as well.
C8,
18.
H18. 96 plus 18. Yep. D. What is the formula for the fragment ion with the mass M and Z value of 85?
Would it be C6H13?
Oh, C6H13. C6H13? The fragment. This fragment is like, you need to show the fragment, whole fragment there. The formula, by the way, okay? So it's be like this. 85 means that it's made of the, it's unbranched carbon, it's made with the carbon and hydrogen only. So there'll be, yes, as you said, it'll be 6 hydrogens, 6 carbons in there. So it'll be like this: 1, 2, 3, 4, 5, and 6, making that into giving 72, and adding some hydrogen there. Now, but because it's a fragment, it will not. This one doesn't have the last hydrogen here. So in the condensed formula, it'll be CH3, CH2, 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 1, 2, 3, 4, CH2, and CH2. Now, when they get fragmentized, they becomes to positively charged. So formula would be positive in your answer too.
Could you do C6H13 please?
No.
Well, so can you explain how you
It's a fragment. You need to show the structure of the fragment.
Can you explain how you get the hexane? Because you do the same thing, right?
Hexane? It's not a
Oh,
hexane.
sorry.
Octane?
For D.
Yeah. 85 is the molar mass of the fragment.
12n plus 2n plus 2.
Or we can think like C and H to n plus 1.
What's plus one?
Hmm?
What's plus one?
Because it's
Fragment. Fragment means it doesn't have the last carbon with the hydrogen. Fragment means it lost.
Oh.
Hmm?
Don't just write H3, right?
H33.
For condensed formula. I'm not like, I can't
Condensed formula is like C6 what?
no, not condensed, right? Like just CH3, CH2, CH2.
Yeah.
I just write H3. See, what is it?
What do you mean this H3? This one here.
Like the left,
The left, yeah, CH3.
like, I just write H3, C, CH2.
Can you repeat that again?
Just write H3C.
H3C?
Yeah, because that's like H comes first. No?
like H3C.
Oh, to show the
CH3.
carbon bond.
No, it doesn't have to. For this, yeah, for this. For the condensed formula, you don't have to worry about that in order. But the structure formula, you do. Okay, that's how we can get the information. All right, just quickly have a look at the samples what we have and then finish the lesson with that.
Thank you.
The sample we have. Okay, guys, sample from sample A to Z. Now this time you are, I want you to, okay, let's have a look at sample B. Sorry, sample C here. Sample C. Sample C. Yeah, this shows you all the things we learned today. Everything means it shows that saturated test with the using bromine water. Okay, it turns sodium. The solution turns colorless. What does it tell you? It's alkene. Okay, it tells you the orange color remains with the oxidation test. It means it's not pretty much nothing. Carboxylic acid test, no bubbles. So confirming the functional groups alkenes here. So even that infrared spectrometry shows that alkene structure. Now what we can get from there is, now we get 70 at the end for the molar mass value. So you have an alkene with the molar mass, but before I finish here, the only information we can get from this is we don't know whether this alkene is branched or not. Do you get what I mean here? We don't know whether alkene has the methyl or like some other things attached or not to. That's what we're going to do next week using these HNMR, CNMR, HNMR diagram here. Next week one is more complicated than today's one.
ppm.
Yes. All right. See you all next week.